Now, if you do have questions, you know how it works, raise your hand, ask them in the chat, or even better, open your mic and ask them directly to Jeff. So Jeff,
Yeah,
if
I'm going to go ahead
I
and try
think,
and find my,
perfect.
yep, should have overridden yours now.
Yes, perfect.
Okay. Right. Well, good morning, good afternoon, whatever time zone you happen to be in. Glad to be back. Wait, so that's not today's not the 18th. Today's the 16th. Sorry. I was
Yeah.
preparing for the
Your
lecture
next one.
on Thursday and got a little ahead of myself here. Sorry about that. Sorry. Today is the 16th. I'll change that in the version that I make available. Right. Okay, so this is a more of a seminar style than as much of a class, but it's also designed with time more carefully in mind to be done in about an hour, even with some questions along the line. So please do feel free. I've changed the title just a little bit to indicate, so I'm going to be talking about this lubricated to frictional transition as a central idea in what we think of as the basis for discontinuous shear thickening in very concentrated or dense suspensions. But I'm going to first say some things also about normal stresses. Why? Well, because I have the floor and I can, and I think that they are an incredibly important aspect of rheology in general and in suspensions especially, for reasons that I will just touch upon. But they also then provide a deeper insight into the phenomena that are taking place inside the suspension. So I want to try to highlight those ideas. Okay. So just to remind people that suspensions can be studied in a lot of different ways over a lot of different conditions and concentrations. So they can be studied by simulation methods on the far left. This is all work that's been from my lab or labs that I've been associated with. So up the upper left, oh, sorry, let me go ahead and get a pointer while I'm early in this effort here. If I could get the system to allow me to do that. Sorry, it's not
Well,
quite.
we do see your mouse,
You do
your
see the
cursor.
mouse?
Yeah, yeah. So
You do? Okay,
yeah,
that's fine. That'll work. Okay, so in the upper left here, we have a condition where the particles are actually at a concentration of about 8%. It may not look quite like it, but this is a Stokesian dynamics simulation. I talked last time about the ideas of how Stokesian dynamics, the simulation works. And so these particles have an interparticle attractive force, which causes gelation. I'm going to be talking about the case here of very concentrated suspensions where these yellow lines are indicative of contact forces between the particles. And so that's an issue that is associated with the development of frictional interactions. And then at the bottom, something I'm going to talk about more next time is actually considering the flow of particles under inertial conditions to try to understand phenomena like you see in the bottom middle, where in experiments, very interesting things have been seen in classic flow scenarios for when you consider them for a multi-phase flow of a suspension. And so the middle is the classic Taylor-Couette flow, but I'll talk about this next time, where there's actually this is pretty highly loaded with particles, about 30% particles, and you actually get a different set of flow states than for the fluid mechanics of the system is actually a different dynamical system than it is for a pure fluid, and for reasons that to this point are not known. So the last that I'll point out is up here is a case that from a lab in Toulouse where we're looking at jamming of particles, and you can see the arching of particles across these are particles that are submicron, so over a quite wide range, they're arching across here and develop these jammed zones in front of, or clogging, it will, it's more one of these very narrow channels. Ultimately, though, I want to say that the systems on the right here, they happen to all be gray. That's maybe an unfortunate choice of pictures, but really we're trying to understand how to develop the flow modeling and the insight to be able to improve on, in particular, engineering flows or geophysical flows, right? So here you have cement, well, it's actually concrete. Below is actually a cement where someone has left their mark with their hands. And then down at the bottom, you can see this is what's called a mud volcano. But mud is a classic example of how you take a granular material, you add fluid, and you have the suspension. So really trying to understand the issues that can impact on our ability to understand these systems and model them is the driving goal. So going back to something I brought up last time, this picture of the suspension viscosity here, where you see that it's undergoing orders of magnitude change. So I've lost my cursor. Sorry, I can't even see it. Well, so this lower left picture. So we talked last time about how the particles, by their rigidity, so single particles, their rigidity leads to this formula at the upper left, the Einstein viscosity, the leading order effects of the particles to increase the dissipation of the material is one way to think about it. But it's because of the forces at the surface of the particle resisting the motion of the fluid that we get this behavior. So that's Einstein viscosity. And then there was a lot of work over many years that led to the realization that there was a standard sort of form in which you had a divergence at a jamming fraction in the way that it's talked about now. For those who are familiar with suspension mechanics, this jamming fraction, or phi j, is often called the maximum packing fraction in the suspensions literature. But so the material goes from obeying something that's close to the Einstein viscosity to the left, where you see the increase, and then it diverges at some maximum packing fraction, which here I think was 64%. So that's a viscosity that is only dependent on the volume fraction. But that's not really the way things necessarily work. And so here, the viscosity as a function of the volume fraction is plotted as a function of the dimensionless shear rate, or the Peclet number. And so what we see is that there's this increase as the volume fraction goes up, but then the material starts to exhibit a behavior that's more complex in its rheology. So you see the shear thinning at low Peclet numbers, or lower shear rates, and then a shear thickening. So we're going to spend a lot of time talking about the shear thickening, but I want to spend a moment here in thinking about the shear thinning. So the shear thinning here is the result of the fact that I have two contributions to the viscosity. I have a contribution which is due to hydrodynamic interactions of the particles with the fluid, of the hydrodynamic viscosity, which is the extension then of this Einstein viscosity. And then I have another part, which is because the particles are Brownian and they have an equilibrium distribution. So when I shear the material, I distort the system, and the system will try to get back to that equilibrium. So I distort it, and then there is an entropic force, effectively, that tries to bring it back to the equilibrium. And so what happens, the reason the system shear thins is that the stress is always going up, and the Brownian stress is always going up until it reaches the maximum it can. The system can no longer keep up with the flow. And so it's actually a saturation of the Brownian stress such that it doesn't grow linearly that leads to this type of behavior. So there is a tendency to say the Brownian stress goes away. That's not true. The Brownian stress always increases as I increase the rate up to a plateau level. But what happens is, instead, if it were Newtonian, it would just continue to grow linearly with the shear rate. So it's the plateauing of that leads to the shear thing. All right, so I wanted to bring that up since this is class format, so just to give an indication. So if you have an idea of the forces in the system, you can generally rationalize these type of flow curves. And so if you have a flow curve that you can't rationalize, the chances are that you don't have a very clear understanding of the forces between the particles, and so it makes it an interesting research question. All right, so we're going to talk about the shear thickening, as I said, but let's remind ourselves of something that came up last time, which is this work that goes back now almost 60 years, right, to 1965. And even then, it was a compilation of a large number of studies where people had been looking at trying to describe the viscosity of a hard sphere suspension. And what they found was, while you could get reproducibility within one set of experiments, there was very often a large scatter between different laboratories for very similar seeming materials, right? And so these were all materials which were designed to be basically hard spheres in a Newtonian fluid. And so it suggests that there were a couple of possibilities. One is that there were different forces between the particles. And so there was a lot of work done. In fact, if you go and look at this paper by Thomas, what you'll find is that it was described in terms of a complex polynomial description in terms of the volume fraction to collapse the data. But in fact, I think that that's now we'll realize that's kind of backwards, because a power series description, I'm sorry, a polynomial description is trying to extend from the low volume fraction end. But the behavior that we're seeing here is really controlled by the fact the jamming fraction of the systems is changing from one system to the other. And you can see that, in fact, the lower envelope looks like it's going to jam about 60%, whereas the upper envelope looks like it's going to jam at something above 70. Certainly, it has more. We want to think about issues like this today. So let me know if you have any problems, because it says my internet may be unstable. Okay, but so there's an even more puzzling. Go ahead.
No, you're very able to take breaks and wait for a connection to come back, actually. So yeah, no problem.
Okay. But so this extreme rate dependence was for very many years a puzzling set of behaviors. And so the shear thickening in particular is what I want to talk about here. So there's another piece of work that I'll bring up that was really seminal, but these two pieces are very nice to look at, because you see, going from 9% to 50% in this work by Laun, that this is actually an aqueous system, particles that are 125 nanometers in radius. A is the radius here. You see the viscosity goes up and up, but stays almost Newtonian for a certain set of volume fractions. That is, it's flat with respect to this dimensionless shear rate, or the Peclet number. But then at 50%, it shows both the shear thinning behavior, strong shear thinning, and then a viscosity rise with essentially discontinuous in the highest curve. Okay, and these were particles which were carefully tailored to be hard sphere in nature. If we look at the right, then this is a very influential piece of work, at least in of the field, and this was coming from the lab at ESPCI in Paris. This was Henri Van Dam's lab, and the work was done by Didier Lotens. So in his thesis work, Didier considered carefully silicals that were either roughened or not roughened. And these were the cases where they were, I think, not roughened. But what we see is at the top, the shear stress as a function of the imposed shear rate, and below, following on the same axis of the shear rate, is the normal stress, the first normal stress difference. Okay, and so I'll define that actually on the next slide, but it's a normal stress effect, meaning it has to do with the thrust that the material exerts on the boundaries, or the plates, if you're shearing the material. So what we see is that as we go to higher and higher volume fractions, the behavior of the suspension in the upper right is going from these curves which go up with a continuous slope, and then they undergo a kink. Right? And so the kink means that the stress is rising faster. And so this is the shear thickening transition. And so this moves to lower and lower shear rates as we increase the volume fraction. So the volume fraction is lower for the curves that have a kink at the right, and lower for the ones at the left. And at the bottom, what we see is that the normal stress, the normal stress difference, which is not quite zero, but very near zero until the transition of the viscosity, you see that it's negative for the lower volume fractions with a sharp turn to significant values. And then at higher volume fractions, then it turns to be a positive value. So puzzling behavior. And so one of the things that I want to point out here is me spending most of my time talking about results in terms of the viscosity and the shear stress. But in fact, the viscosity isn't everything. And in some ways, it maybe isn't even the most important thing in the rheology. And so thinking about the normal stresses is rather important. So the normal stress difference that I just talked about, and one is defined here, but let me go to the left in the picture here, where we're considering a group of particles in fluid, liquid, being subjected to a shear stress. So that's the sigma xy, that's the bulk shear stress. And that's related then to the shear rate and the relative viscosity, right? So that's the typical way that one defines this in a sense where I've scaled out the viscosity, right? Then I have the thrust, and if I have a suspension, hard sphere suspension, it tends to have a thrust outward in all directions, meaning the particles would like to spread, right? So the particles would like to spread, or they have a dispersive pressure, just like I have a positive pressure pushing on me here, right? Now the fluid, because of incompressibility of the entire material, if I have an outward stress from the particles, in fact, the liquid would have to fill in the space. And so that means you can expect that there's an opposite stress state for the normal stress for the fluid. Okay, and we're going to show that that's an interesting that there's an interesting result that comes of that. So the first normal stress difference then is the difference between the thrust in the flow direction, which is here x, and the gradient direction, the y direction up the page. And N2 then would be the difference between the y-directed normal stress and the value out towards you in the vorticity direction. Now, in thermodynamic sense, the osmotic pressure, and for a Brownian suspension, there is actually a true osmotic pressure. There's a true osmotic pressure, meaning it's a thermodynamically well-defined quantity related to the pressure-volume relationship for the particles. But in a general sense, this is mechanically defined, and so the particle pressure is then the mean normal stress with a negative sign, and a negative sign is such that a dispersive pressure is defined positively. That is, a pressure that we would like for the material to spread is defined to be a positive pressure. Let me just pause for a moment and see if there's any questions at this point. I'm sorry, I was pausing. I wasn't trying to move forward, but I'm still trying to figure out if I can get a pointer, but it seems pointless to get a pointer.
Because we don't see your cursor
Any
anymore.
questions? Right. I could kick out and then see if going back in would help. Let me try it.
Oh, we've seen it for a
Now it's going to
second
allow me
there.
to get it also for a second was allowing me to try to get a pointer, but oh, here it is. I'm going to get a pointer right now.
Perfect.
And now I can do it. Okay. So there were no questions then? It's all perfectly
Seems like
clear then.
that.
Perfectly clear.
Perfectly clear.
Okay.
Thank you.
Yes. All right. So the point I'd like to make with regard to the impact of the normal stresses is that this was a major influence on understanding of suspensions over a number of years in terms of the particle normal stresses and their relation to particle migration. So let me describe the particle migration in terms of a system which actually has osmotic pressure. So that's a system of colloidal scale particles, Brownian particles here, 2 microns in diameter. This is work that was done in the lab of Eric Weeks, the collaboration we had some years ago. And so this is in a little micro channel where one dimension is 50 microns. And using confocal microscopy, what was done was to take many images of this under a pressure-driven flow. So the material has a pressure-driven flow from left to right, I think. You couldn't prove me wrong anyway. And what we see is as we increase the flow rate, that is, we're increasing the shear rate on the material and therefore increasing the Peclet number, the particles go from being well dispersed across the channel, although they do tend to flow in lines. You see some chaining of the particles. And then the bright spot in the middle is because the particles are accumulating at the center of this channel. And as you go to higher and higher flow rates, that accumulation gets stronger and stronger. And so you can describe this then as that the flux of the particles is related to the variation in space, and in terms of the way the variation is taken, it says the divergence of the particle stress. And that's about equal to the negative of the group of the pressure. Remember, the negative sign came in the definition of the pressure. And so using that, then the data here is shown in the circles, and different forms of the model with little tweaks are shown here. And so this comes from work that was in these two papers back in the 2000 to 2010 period. And so this can actually be rationalized in terms of the fact that the particles exert a hydrodynamic pressure that then is by the thermally driven motions, right? And so those are the competing factors here. So a key point that one always has to think about in doing any engineering of these type of systems or trying to understand their flow phenomena is that the particles don't go along for the ride. You have to figure out, you have to keep track of the concentration field of the particles. And so what I've spent a lot of time in my life, if you will, my career, is trying to understand and rationalize these type of behaviors in ways that allow us to build a fluid mechanics. And that's part of what I'll talk more about next time as well. All right, so the general idea here then is that there's different pressures in particulate mixtures that take place, that one can have. So you have the osmotic pressure at equilibrium, particles moving to thermal motion, and therefore, in order to keep them in a volume, I actually have to apply a force, and that force is the osmotic pressure times the surface area acting on. Then there's also for granular materials, there's granular dilation. So this is an idea that goes back to Reynolds back in the late 1800s, and here it's driven by shear. It's caused by shear-driven contact stresses. But it turns out that in between these two, if you have particles which are neutrally buoyant, you have what's just called now a particle pressure. It's been, this is sort of a standardized terminology. And this can be driven both by KT and shear. That is, there can be a thermal contribution and a shear-driven contribution. But in particular, there can also be a contact and non-contact contribution. So it's not necessary to describe the particle or consider contact as taking place, because hydrodynamics in competition with Brownian motion can lead to this type of behavior. All right, so here we see the classic U-tube osmometer, and here what happens is that if I have particles or a solute in the liquid, the solvent is sucked across this semi-permeable membrane. It's literally sucked across until the added head here balances the osmotic pressure. And just this is an incredibly powerful force in nature, because the osmotic pressure of seawater is about 27 atmospheres, meaning that this would have to be on the order of 250 to 300 meters tall to balance that, right? In colloidal dispersions, it's much smaller because it scales not just as KT, but as the number density. And for colloidal particles, they're much bigger than molecules. Okay, so if we then consider the particle pressure, the idea is that we have, instead of a semi-permeable membrane, we just have a screen which keeps particles in this gap. And then we ask what happens to this meniscus. And then the third case is, and I'll show an actual experiment of this, so let me rush along a little bit here. But then if I have granular materials, this is an experiment some of you may have seen. I don't know, but if you take a balloon or a bladder, a rubber bladder, and you fill it with sand and water, and then you put a glass pipette into the top of it, what you'll see is, and fill with some more water, what you'll see is if you squeeze the sand, if it's done nicely, you can get this to happen, is that you squeeze the sand, but instead of the liquid being pushed up, it actually goes down, because you dilate the sand, and the liquid then goes down inside the material. So if you're interested in some interesting scientific writing, you can go back to Osborne Reynolds' paper in 1888, I think it is. It's easily available online, freely available. And he actually describes how if you step on wet sand, you'll see around your foot that there's a white region, that it's actually drained the liquid under because you expand the sand. So the we don't usually say such things in our papers these days, but it's actually an interesting thing. But let's see an actual experiment of the middle phenomenon. So this is a cuette device, steel in the middle here, inner member, and then outside it's a polymeric material with two holes punched in it, across which one has a screen, and so there's a picture of the screen, which is smaller than the size of the particles, and so that screen will hold the particles in. The other hole is actually open, and so what I want you to see for this is 45% particles, and you can see the upper level of the suspension here is about the same as these two meniscus levels. One is from the open hole continued over to this point, and the other is from the screened hole. Okay, so I'm going to hit the button, and I want you to watch these two meniscus levels. Ready? Everybody ready? Okay. So when I hit that and I started the rotation, what happens is the fluid that is associated with the screened hole is sucked into the volume here. So it's sucked across into this volume, whereas actually the open hole, that went up slightly. Okay. And so that means that the fluid, when I shear the material, the particles would like to spread, but the only way that they can do the same as spreading is to pull liquid in and dilute themselves, right? And so there's a dilution factor associated with pulling liquid across the screen. You may now see it going up. That's because the shearing was stopped, and then it's just hydrostatics is bringing the liquid back up. But there's actually some particles which spilled out here. So the particles are driven to spread, but when they're confined, the only thing the system can do is suck in liquid, right? And so if you think about this, I think it makes some sense that the fluid and the particles are in opposing normal stress states. And that's a point that I think was very limiting, is that when people try to add stresses to things which cancel one another, lead you to ignore it, right? And so I think this is something to keep in mind. Okay, so we can understand that's not supposed to go over there. There we go. Hang on just a second. I think my my keynote just died. So let me restart it here. Yeah, viscosity is everything. All right, okay, there we go. Let me see if I can get back to the same place. Sorry about that. Okay, I have a pointer.
And sorry, I have a quick question about the previous
Okay.
experiment, but we don't see your screen anymore now.
Yeah, it keeps dying.
Oh,
Keynote keeps dying. Let's try without the pointer this time. So can you see it right now?
yes.
Yeah.
Okay. All right, so I'm going to try to play it again, but if it fails, I'm gonna walk through it, discussing it
Yeah.
without going
Yeah.
to the slideshow.
Yeah.
Oh,
No,
died.
okay, I'm gonna have to do that. Yeah, so
Maybe it's that single slide for some reason. Like if you try to go to a different line.
it could be right. Could be a message in that. All right, so let me just work through this, and then I may try it again on the next slide or so. Okay, so we can understand where this comes from, and this is somewhat relevant to thinking about any non-Newtonian rheology and suspensions, is to realize that if I had no flow, then I would have a spherically symmetric distribution of particles around a particle that's centered at the middle. Where it says no flow here, this is the excluded volume region for a particle, and so it's just the diameter equal to the hard sphere diameter. And then there's an accumulation of particles at contact and excluded volume peak. So it's a standard result that one would have in a hard sphere liquid. If you shear the system as you see at the right, this is at a modest Peckley number. I think it was 25 here, the one in the middle below. You see that elevated region is pushed up against contact on one side and stretched out on the other. And then there's a region where there's actually a wake with no particles seen. That is, one particle over, this was several hundred strain units, there would be no particles at contact there. And so if we then plot this, what we see is that the value near equilibrium, a Peckley number of 1, shows just a slight distortion from being a constant value at the contact surface. So theta here is defined as 0 along the flow line and then goes to pi as I come around, going from here around to this point. So 0 at this point, pi is here. Sorry. And so what we see is that there's a very large accumulation of particles in the compression axis. Okay. And so if we look then at the hydrodynamic sign map, so there's papers describing this at the bottom, but what we see is that this here, where the particles are in compression, is giving us an elevated particle pressure. And over here, where they would be in tension, being pulled apart, then I have a negative value. This is the one that has the highest probability, that it's high probability over this entire region. And here we see none. Then in fact, this is the state that is seen. So contact to describe this is not essential, right? So I wanted to say that first. But the particle, what we realized in looking at suspensions of this sort is that the probability of particles being near contact is extremely high. And so one really has to ask the question, what happens if you allow contact to happen? And so what I want to do now and spend the rest of the time on for about the next half an hour or so is describing a scenario that explains abrupt shear thickening that combines contact friction and hydrodynamics. So I'm going to try to play this one more time because it would be unfortunate if it isn't able to be full screen. So I'll try one more time. Okay.
Yep.
There. Okay. So, people have a lot of fun putting cornstarch in water, and I suspect maybe a fair number of you have played with this in your own kitchen or laboratory, wherever you prefer to do these things. And so here it's as ridiculous to you as it does to me, but it looks like something from a daytime television show here with people, clapping and so forth, watching this guy run on this. But the point is that if this person stopped running, they would sink, right? And so the fact is that the material response is radically different if they're running than if they're not. Okay? And so in the laboratory, we can get an idea of what that means in terms of the material response here. This is work from Jonathan Rothstein, who's actually the president of the Society of Rheology. So for those of you who are not members of the Society of Rheology, here's a plug to go join, right? So here you see the behavior of cornstarch in a rheometer. So it undergoes a shear thinning, which is about a slope of -1 here, and that's suggestive that the material actually has a yield stress at low, if we go to the zero shear limit. But what's of interest for us right now is that the material undergoes this very abrupt upturn in viscosity, and that it changes its viscosity by more than an order of magnitude. Now, the cornstarch turns out to be not the most easy material to study from a theoretical or simulational point of view, because the particles are not spherical and their interaction has some complexities that are not exactly fully describable by the model that I'm going to talk about. Okay. However, this system, which is just Brownian spheres in a low molecular, they're silica in a low molecular weight polyethylene glycol, such that it's effectively a Newtonian solvent, shows this abrupt shear thickening behavior as we go to the high volume fraction. So this is from the group of Norm Wagner at Delaware, and they've done a great deal of extremely nice experimental work on these systems, in particular for systems which are colloidal hard sphere type of systems. And here you see that the particles are of radius 250 to 60 nanometers, so quite small. All right, so what's interesting from the perspective of thinking about the behavior here is not only that as I go to higher volume fractions, I get this higher, stronger and stronger shear thickening response, but also it moves to the left in terms of the critical shear rate, where the onset of the shear thickening occurs. And so if you then replot it, as the authors did, in terms of the shear stress that's applied, that onset occurs at the same stress regardless of the volume fraction, right? And so that's the bulk stress that's applied is leading to the onset of the shear thickening. And that's suggestive of the fact that this is a force-induced mechanism rather than something that's truly associated with a rate, right? Because as you go to higher volume fractions, the rate can be lower. And here at the lower right, we see that that can be rationalized in terms of the stress, which is related to the force on any given particle in the system. Okay, so I'll return to that point. So I want to make some definitions, and this is using our own simulation data just to have clear pictures. So at lower volume fractions, some of the shear thickening can be described based on that accumulation of particles in near contact that I described when I was talking about the particle pressure, and then as weak or hydrodynamic in most of the discussion these days. Then we get to what's called continuous shear thickening, where it's not rationalizable by the hydrodynamic effects. That becomes stronger and stronger until we get to the DST, or the discontinuous shear thickening, where the material can actually be in one of two states at a given shear rate. So it rises discontinuously in its stress. Okay. Okay, so I want to go back to simulation by the Stokesian dynamics method, which I think is really the gold standard for describing hard sphere suspensions and suspensions with extended range forces, because you here have careful description of the hydrodynamics by a method that I described last time, and you have the Brownian motion captured in a way which is again fairly rigorous, right? And so what's seen here is Stokesian dynamics simulations. These are the work of David Foss, but are very similar to some earlier ones of Tan Feng. So what's seen is that the material gets more viscous as I go to higher concentrations, and I have a shear thinning behavior. And I have very close agreement between the filled symbols here of Stokesian dynamics with two sets of data coming oddly enough from two of the Low Countries, one from Belgium and one from the Netherlands. And then at about a Peclet number of 10 here, then the material undergoes a shear thickening transition. And the experiments and the simulations are in pretty good agreement. The experiments start to show a steeper rise. But the key point that I want to point out here is that this is a very weak shear thickening, because this is linear on the viscosity axis and logarithmic on the Peclet number or shear rate axis. And so this rise is only a factor of 2 or 3 in the viscosity, the relative viscosity relative to the pure fluid, as compared to 3 orders of magnitude in the shear rate. So it's a very shallow rise in the viscosity. But now you see this paper here, Dahan et al. 1993, they had some other data, right? So there was other data. The data that's compared to is inside this big oval, and it's from the region where hydrodynamics dominates. And Stokesian dynamics captures that extremely well over basically 7 orders of magnitude here. There's 7 orders of magnitude in the shear rate, and the agreement is exceptionally good. But when we get above this concentration, something happens. In fact, the material becomes strongly shear thickening. And not only that, it exhibits behavior when you get to this 57.5 and higher concentrations, where you can actually see the shear rate go backwards, go down, and then the system doesn't seem to be able to flow at anything except a single shear rate above 59%. Okay, so what's going on here? Okay, and so what's going on here, there was a big clue to this going back to work of Melrose and Ball in the mid-1990s, where they showed doing extremely careful simulation where there were no other forces besides fluid mechanical forces between hard spheres. Okay, so they've worked very hard to do careful simulations of these hard spheres in a Newtonian liquid at Stokes flow conditions. And using many different integration schemes, things from a class we once took that terrified us or something like this, right? They found that no matter what, the average gap between the particles in less than one strain unit at 51% particles, which is well below a random closer, went to very small numbers. So the gaps to incredibly small, 10 times the particle size. And what they effectively showed is that hydrodynamics, when the concentration is high enough, cannot keep the particle surfaces from to values which are below any continuum level. And at this point, the simulation continued. It just wasn't possible to continue the simulations any farther. So this says that we need something else besides hydrodynamics, because 10 to the minus 10 times the sun only have a micro, well below the size of an atom. Place.
Understood. Oh,
It came back.
Perfect.
Okay. Sorry, we lost you there for a
No
moment.
I don't know what happened. Sorry for that.
It's
Okay. All right. So going back to this work of Loughton's, one reason it was so influential is that it showed that just by the very smallest amount of roughness, on the order of 0.6%, there was a radical change in the behavior of the suspension. So you'll have to take a look at the paper. But in recent years, here's some work from Lillian Shao, who we just found out yesterday was the Metzner Award winner of the Society of Rheology. So this was Lillian's work as a PhD student at Michigan. And then there's work from Lucio Isa's group by Shu showing something similar, where you can now tailor the roughness of particles. And so there's a lot of work that's going on to try to understand the influence of this type of roughness on the behavior of suspensions. But we wanted to consider it sort of from the most basic ingredients when we got started in looking at this. And so we just said, what happens if we allow particles to make contact and have frictional interactions? And so we used discrete element model and then put in lubrication interactions between the particles. So this is effectively like taking Stokeskian dynamics and allowing contact to happen, but then simplifying the interactions such that I don't have any long-range hydrodynamic interactions. The only interactions that I consider are those lubrication flows in between the surfaces. Okay, and so we talked a little bit about that last time for those who were online for that. So in this simulation, we have three types of forces. One is lubrication forces or hydrodynamic, so FH in the equation below. Then we have a contact interaction, which includes friction. And so this follows the classic DEM or discrete element modeling, going back to the work of Kundal and Strack. And then it's sort of critical that we have a stabilizing repulsive force in this model. You have to have some force which keeps the surfaces of the particles from coming into contact under low shear rate conditions. So that's FR. And so we balance force. This gives us an equation of motion for the system. So you balance forces, you also balance torques on every particle. So this is an equation of motion because the hydrodynamic force depends upon the motion, right? So this is an equation of motion for the system. And so I'm going to describe some simulation results now, just the basic scenario, where these can be done either under control and measure the stress or sample the stress, or it can be done under an imposed shear stress where we then determine the rate as an output variable. And so you'll notice that the picture shows some slight paucity because we don't want the particle to chain up In the early experiments that I was showing in a microchannel, that they tend to like to do that if they can. And then we have periodic boundary conditions in all relevant directions. So in 3 dimensions, it's periodic in X, Y, Z, and I'll also show a little bit of, I think, 2-dimensional results in a moment. Okay, so there's some papers at the bottom, one that has Brownian motion, another that addresses the influence of attractive forces, but those are not going to be talked about today. I'm just going to stick with the simple model that I showed just before for non-Brownian systems. All right, so to say a few words about each of these forces, I'm just in a way reminding you of things that came up if you were here last time, that the lubrication force for the particles coming along line of centers, or the squeeze mode, induces a pressure-driven flow out of the gap, and that leads to a very large force, which scales as 1 over the gap size. So the force goes as 1 over the gap size times the velocity. And the tangential mode has a much weaker singularity, which goes as the logarithm of that same gap. So that leads to then basically the lubricated interaction has a much easier motion tangentially relative to normal, and that's the basic idea of lubrication. So we regularize this to allow contact to happen. That is, we put in, instead of just 1 over h, it's 1 over h plus some small length scale, which will be 10 to the minus 3 times the particle size for what I'm talking about here, a being the radius of the particle. And then we activate friction with a friction coefficient mu when h goes to 0. So when the particles make contact, which they're allowed to do then without having an infinite lubrication force, because we've regularized that force, then we impose a frictional interaction. Okay, so there's that length scale. And so friction in the usual way prevents sliding, and so it ties together the normal and the tangential forces through a rule that is the Coulomb law, saying that if the tangential force is less than mu, the friction coefficient times the normal force, then they don't slide. They can roll against one another, or they can move with a non-sliding contact. But if then the tangential force becomes larger, then they slide. And we account for the sliding force with the same friction coefficient. And so here I'm going to just show a little movie of a 2D demonstration showing what happens. If you have no friction between the particles, they smoothly move past one another. On the other hand, for this case, which is not moving very well, it's actually a much more jerky motion even without the electronic difficulties here. But you also, if you see that there are much larger white or gray spaces that open up, and that's a key factor in the influence of friction. So the shear thickening in this scenario is perceived as a transition between frictionless and then frictional rheology. So the lubricated interactions then are frictionless. And so if we consider the case of mu equal to 0 and mu equal to 1, then what we see is you have 2 different branches of the rheology, both of which are rate independent. That is, if I just have hydrodynamics and contact with friction, those are both rate independent in terms of the material properties that one would define. And so then the question is, how does the material make a transition from from one curve to the other? And so the idea here is that at low stress, we reside on the frictionless branch, and at high stress, we transition to the upper branch. And so the material transitions from lower viscosity to higher viscosity. Okay. But what controls that rate has to do with the microscopic physics of the interaction between particles. And so I'm going to apply an electrostatic double layer model for the repulsive forces. So if I have particles suspended in a liquid which have charge on their surface, they will draw a layer of counter ions into the vicinity near them, and that will decay away over a Debye length. And so the force between particles occurs because I'm trying to bring these two charge clouds, which at the lower left are these yellow regions, or the charge clouds around the particles. You try to bring these together, and the system fights back against that. up to a value which would allow the particles to make contact. That's the repulsive force Fr at 0. That's the contact value. So crucially, what this does is that it means that if the particles are pushed together with small force, they will stay well away from each other as they flow past. However, if they're pushed together with a large force, that is, a large stress is integrated up over their surfaces, then they can be pushed together and they reach contact. And so there is a stress dependence or a rate dependence of that behavior. And so that gives us then a microscopic definition of a stress, which is the repulsive force at contact divided then by the surface area of the particles, which scales as a squared. So that gives us a microscopic stress definition. And so if we look then at the response of suspensions in simulation at different friction coefficients, we see that below this characteristic stress, all the curves collapse because the particle surfaces don't see one another. They're kept apart for stresses that are small compared to this value, which is sigma naught. And once I get above that level, then I see then there's a larger and larger response as I go to higher friction coefficients. And that saturates at values of about a friction coefficient of 5. Okay. And so if we compare then with experimental data, this is a comparison where the friction coefficient is actually 1, I should say. That's not shown here. This is against some other data from Norm Wagner's group. And what we see is that with a slight shift in the volume fraction and fitting the data at 56%, I believe we did this, 54 or 56, that we get good agreement across the range of behaviors. The shift in volume fraction is actually because our system is slightly polydispersed, and so the blue data, our data, is at a higher volume fraction because you can pack particles a little more efficiently with the bidispersity. Okay, so I'm not going to go into the details here of the corresponding colloidal force description. But the overall scenario then is that as we consider higher and higher volume fractions, we get a stronger and stronger viscosity response, or if you will, you could plot this in terms of stress as well. And we get the same behavior regardless of whether we're stress controlled, which is the black data here, versus rate controlled, which are the blue plus signs, right? But once we get to the case where we have discontinuous rise, that's at 56% volume fraction, then we actually can only characterize the behavior through a stress controlled simulation. So the highest volume fractions are stress controlled. And so we see that there's an S-shaped curve, which is indicative of the fact that the material is bistable. It can be stable at a higher and lower value in this curve. And there is actually observed hysteresis. If we look at the behavior going up in shear rate, it will jump at one point. As we reduce the shear rate, it will come back down at another point. The final set of behavior here, so the S-shaped curves are shear thickening curves, discontinuous shear thickening curves, I'm sorry. But if I go to 59 and 60%, the material actually shows a behavior which is jamming. That is, if I flow at low stresses, I have the viscosity will be increasing. The shear rate will be increasing and the viscosity actually decreases a little bit here, but then it will turn around and go back to lower shear rates. That is, the material will actually jam under the higher stresses. And all of this is captured at the lower right in a flow state diagram, which is actually attributable to Mathieu Viard and Mike Cates. And so the idea here is that we have the dimensionless stress on the left axis scaled with this sigma naught, the microscopic definition of stress, against the volume fraction. And so we see at low volume fractions, we have just continuous shear thickening, and that's what's seen in the 45 and 50% over here. But when you get to the 56%, then the material undergoes discontinuous shear thickening. And so this region inside the dotted red the material at a given shear rate would jump across from one stress to the other. So this is like a two-phase region in a thermodynamic sense. But when we get above this line, the dark line at about 58% here, or 0.58, is actually the jamming fraction for the friction coefficient. And so now the material, when it starts to undergo DST, that is the discontinuous shear thickening, it actually shear thickens to an infinite viscosity, which means it jams. And so this captures the behavior, which is the 59 and 60% over at the left. So underlying all of this behavior is some sort of microstructure. So at the beginning, we talked about microstructure in terms of pair distribution function and organization in that way. But here, because the particles make contact, there's actually a different sort of structure that's worthwhile to think about. So at the lower left, you see both a snapshot of the configuration and the force chains in the system. And these are aligned along the compressive axis of the flow. So it's being sheared to the right at the top of these pictures. And then when we go to the high viscosity state, which is up there at a viscosity, relative viscosity of about 1,000, what we see is that you don't see any change in the sphere pictures, the configuration, but what you see is a very large change in the force network. So the network has become ramified in all directions here. And so we can see this in 2 dimensions here as we increase the stress in some movies. First, at low stresses in the upper left, you just see lubrication interactions forming chains. And so the lubrication interactions are what were known as hydroclusters, are the incipient structures that then develop force chains once I get to stresses which are comparable then to the microscopic stress that is describing when I will achieve contact. These then percolate and densify as I go to higher and higher stresses. So this is in 2 dimensions. The basic phenomenology holds for 2 dimensions as well. So you see that these lubrication stresses associated with the accumulation along the compressive axis give rise to the chains that are actually contacting particles that lead then to full evolved force networks. And so there's been a mean field model that developed. It's maybe not quite mean field, but that's the terminology that's typically used by Byron Cates, where they describe the behavior of the suspension in terms of the fraction of particles in the vicinity of one particle which are in contact versus being lubricated. And so this was very influential work in the development of the field. So what we see is that we can fit our data to this mean field model. And then so that's the lines here are the mean field fit to the data that we've simulated. So this is stress plotted as a function of shear rate. So it's a slightly different form than the viscosity. But then we can actually take derivatives of the stress as a function of shear rate in the model. So then we have a mathematical model that we can take derivatives of. And what we see is that at some point, this viscosity, this d sigma d gamma dot, which is not quite a viscosity, it's more of a susceptibility, actually diverges, right? And that's the first place that in the upper left here, we see a vertical rise. That's where DST first takes place, right? That's the onset of DST. And so at a position where, so let me make this point, at a position of about 55.5% or 55.3, which you can see here is between the blue and the black, the system can't decide what it wants to be in terms of the stress at that shear rate, right? And that's very much like a thermodynamic system, which is undergoing a phase transition. So you're then at the point of the second order phase transition. So the critical point behavior is something that we've considered quite a lot. And so if you look at 55%, that's the closest that we had data to what the fit of the data said was the critical point. We can see that as we increase the shear rate, we get much larger fluctuations away from a baseline at first as we go up to this purplish line, I guess it is. But what you see in the blue curve is that it skates back and forth in stress at a given shear rate. over more than an order of magnitude. So the system simply can't determine what it wants to be. Now, if we go to 56%, the system, it's a small system, remember, so it spends a certain amount of time in the high stress state and a certain amount of time in the low stress state, but it can still fluctuate back and forth until the shear rate is pushed high enough. And so in the red curve, you see that it's pushed up high enough to stay in the high stress state. All right, so just to close out then, the stress distribution that you see is goes as you increase the shear rate from all low values with a nice peak behavior here for both 55 and 56%. Then I see the development of these excursions to higher stress as I increase the shear rate. At the critical shear rate, what I see is on the left, the system can't decide what state it wants to be in. It has effectively a flat distribution of stresses as a function of flat distribution of probability of stresses. For the slightly higher volume fraction, the system has a bistable scenario in one of two states, but in between that probability. And then eventually the system transitions over to the high state for either case. But the key point is this is a behavior on the left here, which is very much like a critical point behavior in a phase change system. So in that sense, one can sort of think of the shear discontinuous shear thickening as a driven phase transition. Okay, and that just captures all of that behavior, just showing that 55% has the behavior that shows this transition where there is a state which is unable to determine where it wants to be, versus the 56% is generally bistable. All right, let me close up then, and hopefully there'll be some time for questions. I started out just trying to bring out the idea that normal stresses undergo similar transitions in behavior to what we're seeing here, but also they imply this structural anisotropy, which we can understand, and then it also leads to migration phenomena. The lubricated to frictional scenario for the shear thickening that I've described does give us a rationalization of the behavior. Doesn't describe everything, but I think it lays a baseline for understanding what's going on. And in particular, what it shows is that for systems that are this concentrated, the tribology of particle surfaces controls the rheology of the system. And so this is a place where intersection of tribology and rheology can be very helpful, I think, to both fields in terms of developing understanding. The fluctuations that I just talked about are associated with what looks like a critical behavior. And so the question is to develop that in terms of a phase change analysis. And then the basic underlying structure that has to be thought about then is related to the force chains in the system, which evolve into then this fully ramified force network. And I wanted to say that if you're particularly interested in these dense suspensions, there was a special issue of the Journal of Rheology back in 2020, where a number of papers that from different perspectives were presented, and this was edited by Emanuela Delgado and me, I should say. So with that, let me close and answer questions if there are any.
Thank you, Jeff. Thank you very much. And yeah, people, questions.
There we go.
Yes, please.
Hi, Jeff.
Go ahead.
Here is Chico Rocha from Marseille. I have two quick questions, actually. So in this shear thickening mechanism, what's the real importance of the fluid? So if, in other words, if you had just a repulsive force that prevents contact at low stress, would it also give to a dry shear thickening mechanism? This is the first one.
Yeah, so I think...
Yeah, sorry.
Let me answer that one first, if you can remember your question. Just hold on. So I think yes, that one could see this. So the role of the fluid there are many roles of the fluid. One is that the actual balance and the way that stress is transmitted into a suspension involves the fluid contact with the boundary, or the liquid contact with the boundary. The liquid also plays a role in general in that repulsive force. So not only hydrodynamic force, but it actually is the carrier, if we do this in terms of the ions, in describing the static repulsion. And in order to make careful contact with experiments, no pun intended, requires having the fluid. So on the other hand, I do think that if you just look at the essential balance, then you could get a dry shear thickening, yeah, a dry system shear thickening.
Okay, cool. Thanks. And the other question is regarding this amazing quantitative agreement between the simulations and Wagner's experiments, although apart from the polydispersity stuff. So I come from the dry granular community, let's say. So normally when you do DEM in these systems, you need to kind of, I don't really know why, but maybe because people normally only consider sliding friction and not rolling friction, but you need to artificially increase a bit the interparticle friction to get macroscopic, the right macroscopic bulk friction coefficient. Is it the same case in suspension, or it's a different scenario?
So, well, okay, so when you're talking about the bulk friction coefficient, do you mean the ratio of the shear to the normal stresses in the system?
Yeah.
Yeah, I'm not sure I'm prepared to comment on that part, but we do have to go to somewhat larger friction coefficients than are experimentally measured. And so that says that there's more going on than simply Coulombic friction. And there could be many other issues there that have to do with, for example, a little bit of adhesive force would play a role there. So yes, we do have to go to slightly larger friction coefficients than are experimentally measured. They're in the same range for some of the data, like for example, the results from the group at Annie Colan's group showed values that were on the order of about 0.4 to 0.5. But in order to match the data of their case, we had to go to 1. And so something is not all there. I'm not sure whether rolling friction thing, who I think was here a moment ago, where they've looked quite a lot at rolling friction, and you can radically change the amount of the stress response with the right combination of shear and rolling friction. So that's an issue that's still to be probed further. And some very nice experiments that I've seen been done by Lucio Issa's group actually has looked at rolling friction by putting a cup.
Yeah.
So I think that the basic mechanism has some merit, but is it complete? I'd say certainly not.
Okay, cool. Thank you very much for the lecture, so very nice.
Thanks.
Thank you for your question.
So, hello, Jeff. So I have a question regarding the phase transition that you talked about. So, when you are saying that this is a kind of phase transition, are you saying that this is actually a phase of the fluid or the suspension?
Well, it depends on how far out on a limb I want to go. So what I guess the question is, what do we mean by a phase? I think it's saying it's in a dynamically different state, and that state has characteristics where the transition has characteristics which have the hallmarks of a phase transition. That is, the fluctuations that are associated with this, which are very much like what one sees in critical state behavior, where you have, for example, critical opalescence in a phase transition. So, and that's associated with the fact that the system can exhibit macroscopic or full system correlation, not correlations that are at the microscopic length scale, which would be particle length scale. It goes to much larger length scales. On the other hand, what I will not say is that we have an understanding of, sorry, it says, can you still hear me?
Yeah.
Yes.
It's okay. So I will not say that we have an understanding of this in thermodynamic sense, because in thermodynamics, one can understand phase transitions in terms of a balance between energy and entropy. And we don't have that understanding right now. However, I will say that trying to figure out that set of ideas has been the driving motivation for thinking about these things for me for very many years. And the dynamic thought processes are quite helpful. They have driven the understanding and pushed the questioning in the right direction, but we don't understand the system well enough to say anything about true phase transitions. No.
So like the way, like I understand like phase transition is how it behaves near the critical point. So you alluded to the stress probability, which basically has a bimodal kind of structure at the critical point of that, the way you are defining the phase, and it goes to a like higher probability at some higher like at some point or something like that, like it switches from uniform stress probability or I don't know. Can you
Do
show
you
the
see this
graph
pic?
again?
Are you seeing it now?
Yes.
So there
Uh-oh.
was a graph where you are talking about P sigma, I think, and the P sigma was like uniform uh, at
Right.
certain
I'm
phi.
actually, is anyone seeing my slides right now?
Yeah,
Yeah.
but I think
I
it was
actually
talking about slide 33
have P
maybe.
of sigma showing, but this.
Yeah, maybe this or something later. I don't know.
Well, this is the one that shows P of sigma directly. And so here I have okay, for the 55% here would be the equivalent in a gas liquid phase transition of an isotherm. So it's an iso concentration conditions. And so what I have is a system which goes from at low shear rates, it has a peak at one particular stress, right? And then as I go to very high shear rates, it has a peak at a different stress, but a much broader peak. You can see that, which is suggestive of something, and the peak is lower so that it adds up to unity. But then in the middle, there is this place where the system is simply unable to determine what state it would want to be in, and that would be the critical point of the system. And there, the susceptibility, that is the equivalent of the variation in a gas liquid system of the density with respect to pressure, becomes infinite, right? So I have infinite compressibility. Here, the system has an infinite increase in the stress per increase in the shear rate. So d sigma, d gamma dot becomes vertical. Okay, so if I go back to this point, this is the place where it's easiest to see, is this is like having a two-phase region turned on its side. So the isotherm that would be the critical isotherm is, say, the black curve here, and the two-phase region would be like this. If I was looking at a van der Waals type of system. So I don't think that the van der Waals is the right system, but just to give the ideas.
Right, right. Like, are you like willing to call that phi C as kind of critical point of phase transition? Like it looks like a first
Absolutely. If
order.
you, right. So this paper at the bottom here, this one that Omer Sedis is the first author on down here, that whole set of ideas is developed there in terms of the fluctuations at this position appears to have all the hallmarks of a critical point behavior.
Okay.
So
Okay. And
that-
it
I'm
it
willing to
seems
say
it
that.
looks like first order. It looks
Well,
like
the
having
critical
signatures of
line,
first order phase transition. Am I right?
once you go to concentrations above the critical, yes, but at the critical point, then it's second order.
Okay.
I think I understand my thermodynamics. I could be wrong, but I think the critical point would be second order. I'm a rheologist.
Okay.
No, but I mean, so I think that's the essential idea here, is that it's that the system has what appears to be a two-phase region where it could be in one of two states, right? And so do we know the chemical potential? No.
I think beyond critical point it will be like second order phase transition, and at critical point it will be like first order.
Well, so at the critical point, the two values of the
There is a discontinuity, right? At critical point.
there's just okay, so the derivative here goes vertical, but at only one point at the critical point. Above that value in concentration, there is the S-shaped curve region where, if I go back to this, I've lost it. I can't find the scenario now. Here. So the S-shaped curve, so this is the first place where the derivative of the stress is vertical with respect to the shear rate. This is the viscosity, so it's a little different. But then in this entire region, it's bistable.
So my follow-up
So
question
if you
will be,
think of the shear rate as a variable. Yep, sure.
yeah, my follow-up question will be like, we see phase separation, for example, in some complex statistical mechanics systems, when two phases can coexist, but with a separate kind of occupying separate volumes or separate regions of space or separate parameter space. Do you see that kind of phase separation between shear thickening and shear thinning regions?
No, no, we don't. And that issue of how to think about that point is a central one, I think, in terms of trying to make this analogy. So, but no, right? And one way that could happen in a system like this is it could shear band, but that's not seen in our results here. I'm gonna have to call the questions here because I've actually got to go and take questions from my undergraduate class. They have an exam on Thursday, so
Oh, they will have a lot of questions then.
I hope so.
Okay, well, I'll stop the
So
recording here.
thanks for listening and the questions and the discussion.